Hello Chem 212 students, and welcome back for our second video of this week regarding nuclear magnetic resonance. Last time in our lecture we discussed the principles behind the way the nuclear magnetic resonance spectrometer worked, and we started to discuss some of the important factors on analyzing a spectrum that comes from performing a nuclear magnetic resonance spectroscopy on a particular organic sample. And we, in particular, were focusing, as we left off, on the chemical shifts that would be produced when we have in proton NMR spectra due to the inductive effect of having a neighboring electronegative atom, either directly attached to the same carbon where the proton is, or on an alpha or even a beta carbon, in which these effects will decrease until after the beta carbon they essentially go back to no effect, being more than a couple of carbon atoms away. So another important effect that affects chemical shifts are anisotropic effects. And these occur due to the movement of electrons that are shared between unhybridized p orbitals in a pi bond. So here we have a benzene ring, and that has alternating pi bonds here, so this would be single, double, all the way around. So the pi electrons can circulate throughout this entire ring, and when they're moving about in this fashion, they produce a magnetic field that is perpendicular to the movement of the electrons. And this field will either go in line with the external magnetic field on the outside of the ring or opposed to the external magnetic field on the interior of the ring. So for a molecule like benzene, all the protons are in the exterior of the ring. So that the fact that the magnetic field produced by the electron movement is aligned with the applied magnetic field means that the magnetic field experienced by the hydrogen will be increased, and thus you will observe a larger chemical shift. This is called diamagnetic anisotropy. So what this means, anisotropy means that basically things are different in direction in one part of the molecule than the other, in one area than the other. So the magnetic field on the outside is increased, and the magnetic field on the inside is opposed, or the external magnetic field is supported or added to by this internal magnetic field due to the movement of the electrons, and the internal magnetic field is opposed. And so the proton is going to be de-shielded by this added magnetic field due to the anisotropy. So the result of this diamagnetic anisotropy is you get a significant chemical shift for example, aromatic protons like the one on the molecule we just seen. There are actually 3 chemically distinct protons here, and for the aromatic protons, at least on the aromatic ring, you can see that there's a lot of overlap, but they're all very, very far chemically shifted all the way to like 7 ppm. The remaining hydrogens here are part of this ethyl group, so you can see that for the 2 carbons, this would integrate to 2 and is a quartet. It's a quartet because there are 3 hydrogens on this neighboring methyl group here, or the end of the ethyl essentially. This has 2 hydrogens, and so it would integrate to 2 hydrogens and have a quartet, and then we have a triplet integrated, which would integrate to 3 carbons. So this would, or 3 hydrogens rather. This is integrating to 2 hydrogens. This represents 3 hydrogens. It's these 3 hydrogens right here. You can see that it's not really chemically shifted much at all, maybe just a little bit, because it's 1 carbon away, or rather 2 carbons away, I guess, from the benzene ring. Whereas you do have some significant shifting on these carbons right here, which correspond, or these hydrogens rather, attached to this carbon, which are represented by these peaks right here. So there are some exotic structures like aniline here that have hydrogens both that are aromatic. They have alternating single, double, single bonds, so there can be movement of the electrons through all of these unhybridized p orbitals on all these carbon atoms. But there are on this molecule internal hydrogens. So what we observe for the external hydrogens is that their magnetic field is increased due to this anisotropy, and they have a significant chemical shift due to the fact that it's similar to being de-shielded. They're just experiencing a greater magnetic field, and thus they have a greater separation in energy between the alpha and beta spin states. For the protons inside of the ring, they experience a decreased magnetic field, and so they actually have a negative chemical shift due to that opposing magnetic field, which decreases the magnetic field they experience, and thus decreases the chemical shift. So, in summary, the chemical shifts here can be affected or affected by both inductive effects and this anisotropic effect. So when you have a methyl carbon, this is attached to only one other carbon, it has the lower end chemical shift at around 0.9. The more carbons that you have attached, the more electron density can be distributed and shared and actually kind of moved away from these hydrogens, thus de-shielding them slightly. The more carbons that are attached, the more of this de-shielding occurs, but it's a relatively mild de-shielding. Then, due to anisotropic effects, when you have an allylic hydrogen, that is one carbon away from that's involved in a pi bond, so you get a little bit more of a chemical shift there. This is even greater for a hydrogen that's directly attached to a carbon involved in a triple bond with two pi bonds here. Even greater for a methyl group, so the hydrogen's on a methyl group attached to an aromatic ring. These are all due to the anisotropic effect with the movement of the pi electrons. Then at even higher chemical shifts here, like 2 to 4 or 2 to 5, we have the hydrogens that are, in this case, for the alkyl halide, directly attached to a carbon that's attached to a halide, which withdraws the electrons and thus de-shields the protons. Or a proton directly attached to oxygen, which pulls electron density away from the hydrogen, thus de-shielding it in that direction. Then we have further anisotropic effects. These are even more pronounced when the proton is directly attached to the carbon that's involved in the pi bond. And for a proton attached to an aromatic ring, this is even further enhanced. Finally, we have hydrogens attached directly here to a carbon, not only involved in a pi bond, but also attached to a very electronegative atom, oxygen. So you have both effects going on here, both the inductive effect, but also the anisotropic effect, thus increasing the chemical shift significantly. So aldehydes tend to stick out like a sore thumb because of their extremely high chemical shift in the proton NMR. The carboxylic acid proton is even further pronounced due to its additional inductive effect because of the two oxygens and also the anisotropic effect involved here in the resonance of these electrons between the two oxygens. So very, very large. So this ends up standing out really obviously too. When you have a chemical shift of 12, it will indicate a carboxylic acid. Now, besides the chemical shift, what we'll also be interested in is the integration, or the area under the peaks. And so when you sum up all of the areas under these peaks, these will tell you how many protons that this signal corresponds to. Now, this is going to be different for every spectrum, so we can only compare these in terms of their relative values relative to one another. So when we want to analyze these, what we do is we look for what are the lowest integration values, and we compare everything else to those. So if we look at the lowest integration value here, it's about 27 and about 28. And then the higher integration values are around 40, okay? So we could say that if this were 1, for example, this one is not 2 times. 2 times would be like 54. It's about 1.5 times as big. And this one here would be about the same size as the other one, and this one would be about 1.5 times as big as the other ones. Of course, you can't have half a proton, so we would just actually double each of these. So we'd make this 2, make this 3, make this 2, and make this 3. And that would give us a whole number ratio of protons here in the spectrum. So this does exactly what I was talking about. If you divide 40.2 here by the lowest value, 27, you're going to get about 1.5. So we're going to take the lowest value as being 1. If you compare 28.4 to 27, that's about 1.05, slightly larger. So we're going to go for the closest, like whole number or half or something like that, at most a third probably. And if we look at 42 compared to 27, it's a little over 1.5 times. And so ultimately, like I said, we can't have half a proton. So we're going to double each of these. So we'll call this 2, essentially. We'll double 1.5, call it 3. We'll call this 2, 2 times 1. We'll call this 2 times 1.5, which is 3. And so ultimately, that will get us our whole number ratios of protons, 2, 3, 2, 3. So these integrations, as I said, are relative quantities. They're not absolute quantities. So don't be too disturbed if you see them different on one spectrum versus another. That's pretty normal. When you have symmetry, this can affect the integrations. For example, here, this has both reflectional and rotational symmetry. These two hydrogens here are going to be chemically equivalent. So altogether, these will give a signal that represents 4 protons. And then we have 3 chemically equivalent hydrogens on each of these hydrogens carbons on the end here. So these are chemically equivalent with these ones due to the rotational and reflectional symmetry. So this would integrate to 6 protons, or there would be a 2 to 3 ratio, essentially 6 to 4. 4 to 6 and 2 to 3 are the same ratio, really, just reduced. And so you would see a ratio like that for the proton signals. So here we can see the actual spectrum for the 2-pentanone. And you'll look at it, indeed, we get only 2 overall signals. And you can see that if we divide 48.0 over 32.5, we're going to get a value that is approximately equal to 1.5 here. And so what this is telling us is, this peak here is representing 1.5 times as many carbons as this one. Well, this totally makes sense, or hydrogens rather, not carbons. This totally makes sense because if we have these 4 hydrogens here, these ones are closer to the carbonyl, so they're going to be downshifted more significantly. Here we can see it's about 2.4 ppm, and we're going to get a quartet here because for each of these hydrogen atoms, they're going to be next to 3 other hydrogen atoms. Okay, and so that's why we get the quartet. So then here, for each of these chemically equivalent hydrogens, each of those are going to be next to 2 hydrogen atoms. So each of these 3 red ones here, are next to a carbon with 2 hydrogen atoms. And so those are going to get a triplet, and they're going to be lower in chemical shift because they're further away from the carbonyl, and they're just slightly over 1. They do experience a little bit of that inductive effect, but not all that much. If they didn't experience any at all, they'd be down here at about 0.9. So they do experience a little, but it's not that. So as we've discussed a little bit. In addition, there's splitting patterns, and I've been alluding to this as we move forward. You've noticed that these signals, they don't always occur as a single peak here. Sometimes they occur as doublets, triplets, quartets, quintets, sextets, septet, for example. And so let's talk about why this multiplicity or splitting occurs. So multiplicity results from the magnetic effects that protons have on each other. So they each have their own electrons around them, and those are moving as well. And so when a proton is close in space to another one, the movement of their electrons creates a magnetic field that affects the neighboring hydrogen. And in some cases, the movement of the proton here in the hydrogen B, its direction will be in the same direction as the external field. Sometimes it will be the same direction as the external field, and so there's going to be two different protons, two different basically situations for proton A. Let's say it's either the proton is in the same phase or the same direction here, spin state, as proton B, or it's and the movement of the electrons in the magnetic field that is induced by proton B, or they will be opposed. And so you're going to get two separate signals. Where the spin state is opposed to the magnetic field, you'll have slightly lower chemical shift, and where it's together with the magnetic field, you'll have a slightly higher chemical shift. When you have two neighboring protons, now on the neighboring carbons, now you have two potential orientations of the spin state. So if both of the protons B here are against the field, then you're going to have a lower chemical shift. If they're both together with the external magnetic field, that will increase the chemical shift slightly. And then there's two other positions. One of proton B is with the field and one is opposing, or the other one's with the field, the other one's opposing. That's twice as likely. And so that's why you get this kind of shape for a triplet, is because statistically there are two of these possibilities, up, down, down, up, but there's only one of the down, down, and up, up. So you get this kind of triplet shape. For a quartet, it's similar. If you have proton A, its signal here is going to be split 4 times by these, and that's going to be because there's one situation where all 3 of protons B can be aligned against the field, or all 3 could be aligned with the field. But there's 3 other possibilities of, in a sense, here we have down, down, up, down, up, down, down, where down is against the field and up is with the external field. And likewise, we have two with and one against. So this is 1 with the field, 2 against, and we have 3 different ways of having 2 with the field and 1 against. And so then you get these for this quintet that arises, and it looks like a 1 to 3 to 3 to 1 ratio. So this multiplicity trend continues, and you can have more and more and more peaks. And we analyze the splitting pattern of the signal in proton NMR, and we can, based on the splitting, we can determine the number of equivalent protons on an adjacent carbon. So when we look here, and the table 15.3, by the way, in the book just shows the relative amounts. It essentially extends this and continues for quintets, for for five peaks here, the quintet, the sextet, septet, and so forth. 5 peaks is a quintet, 6 peaks is a sextet, 7 peaks is a septet. So the number of peaks that you have is going to be n plus 1, where n is the number of protons that are chemically equivalent on the neighboring carbon atom. So when it comes to splitting, equivalent protons cannot split one another because they resonate together. And so that's why you're not going to see, for example, when we go back to this example here, because these protons are chemically equivalent to these ones, we do not get a splitting due to these protons here. Also, they're 1 away, so they wouldn't split anyway. But even if they were, we only get splitting due to these ones right here. Chemically equivalent protons do not split one another. And to split each other, protons must be within a 2 or 3 bond distance. So if they're geminal, they will experience splitting. If they're vicinal on neighboring carbons, they will experience splitting. But if there's a carbon in between them, they will not. So the n+1 rule applies for protons that are all equivalent. So the splitting pattern observed below here will be more complex than a simple triplet. And the reason is due to the fact that here, this OH group is on a chiral carbon. And so this is going to mean, and also we have a double bond here. So we have a lot of stereochemistry here that's going to make each of these protons that are not on a methyl group each not be chemically equivalent with one another. So when this coupling occurs, the coupling has peaks that are separated by a constant value, which is referred to as the coupling constant, or the J value. And the J value is the difference between the splitting and the peaks measured in hertz. And when protons split each other, they have the same J coupling constant. So that's not something that we look at all the time unless we want to get into real detail. But when researchers are analyzing their NMR spectra and they're having trouble assigning which peak corresponds, which or peak or series of peaks here corresponds to which protons, they will sometimes measure these J values very exactly and figure out which ones match up exactly to figure out which protons are actually coupled with one another. So in terms of the signal for A, here we get a quartet because there are three chemically equivalent neighboring hydrogens here on this neighboring carbon. And so we get a coupling here, a J value that we've indicated as AB. Then for the protons B, here those have two hydrogens on the neighboring carbon, so they split up into a triplet. And again, that J coupling is also going to be that same value because when those couple, they produce J couplings of the same value. So that's a way that you can verify that two sets of protons are coupled, is if they have the same J values. Now, you might wonder, we talked about at the beginning, given that chemical shift is going to be the same, no matter if we use a stronger magnetic field instrument or a weaker magnetic field instrument, why would we want to use the stronger one then? Since it's more difficult to make a stronger magnetic field, it requires more energy. Why would we want to do that? And the answer has to do with the J coupling. The J coupling, the way it works is the J coupling has a certain number of hertz that the J coupling will represent or spread out over. Well, when you have a higher field strength spectrometer, a chemical shift here is corresponding to a greater number of hertz. And so, for example, here, this chemical shift from, so these both have the same chemical shift. This peak C is at 4, and then if we look at the middle of peak B, it's about 4.3, 4.4. And that's true here too. The chemical shift is a little over 4, and for peak B, it's a little over 4. Let's see, it was like 4.2 to 4.3 in each case. So if we look here at this one, the very middle is at about 4.2, 4.3, right in there. And it's the same case here. The middle is about 4.2, 4.3. And then for peak C, representing these hydrogens here, it's about a little bit below 4.1. But because the right picture here represents the 300 megahertz instrument. So the J coupling is the same amount of hertz in each case, but that occupies more of the chemical shift values in the 60 megahertz spectrometer than it does in the 300. So the larger magnetic field helps you to resolve split peaks better. And that's why chemists and physicists go through the effort of making these superior NMR instruments with larger magnetic fields, is for greater resolution between the J-coupled, the split peaks here. So when we're looking for these splitting patterns, we want to look for patterns of splitting patterns, right? That way we can very quickly determine what pieces of a molecule that each of these splitting patterns represents, And ultimately, we can piece all of these pieces together to get our overall molecule, our overall structure for our molecule. So one very obvious splitting pattern is the combination of a quartet and a triplet. When you see a quartet triplet like this, what this is indicating to you is an ethyl group. We have 2 hydrogens here from this quartet with the neighboring 3 hydrogens, and then we have 3 hydrogens here with a neighboring 2 hydrogens. So we get this triplet here. Because remember, the number of peaks is n plus 1. So in this case, for these hydrogens, their n and n, their number of hydrogens on the neighboring carbon is 3. So you get 3 plus 1, 4 peaks. Here, for these chemically equivalent hydrogens, the number of hydrogens on their neighboring carbon is 2. So you get 2 plus 1, 3 peaks. Okay. So notice that this ethyl group has to be isolated. It has to be an isolated ethyl group. If it's got something else here, that will change. That will change things as well, right? Because this one will be split perhaps by these ones as well. Now notice that again in this, if these protons are coupled together, their coupling constants should be the same. So the difference here, which is J, should be the same as this difference here is J. So here you can see that J here is not the same as J over here. So this would not represent an ethyl group. We can tell because the coupling constants aren't the same. So although we're not going to go into very carefully determining the coupling constants, we will want to pay attention to them if we see an obvious difference. Here in this example, we have an entire tert-butyl group with 9 hydrogens that are all chemically equivalent. So this produces a very large signal representing 9 hydrogens. So that's a real big giveaway with 9 equivalent hydrogens that you probably have a tert-butyl group for. So a very large singlet like this will indicate a tert-butyl group. For an isopropyl group, what you're going to have is you have 6 hydrogens that have only 1 hydrogen on the neighboring carbon. And so you'll get 6 hydrogens split as a doublet. And then for this hydrogen, you'll have 6 neighboring carbons. So you'll get a sextet out of that, or septet rather, out of that. 7 peaks, or 6 plus 1. And so this 1 hydrogen septet, along with the 6 hydrogen doublet, is a clear indication of an isolated isopropyl group. Now, one thing that can occur is when you have 2 sets of protons that are not chemically equivalent to one another, you can get a more complex splitting signal that occurs. You can get a splitting of a splitting. So, for example, for hydrogen B here, hydrogen B has 4 chemically equivalent hydrogens here on this neighboring carbon on the left, rather 3, 1, 2, 3, which would result in a splitting, right? So here we have 3. So if we're focusing on, again, we're focusing here on hydrogen B, focusing right here, and we can see on the left side, we have 3 protons, okay, on the neighboring carbon. So our splitting, we expect n plus 1. Here it's 3, so 3 plus 1. We expect a quartet due to this splitting. But on the right side, we've got 2 hydrogens. And so that's going to split it n plus 1. It's going to split it. It's 2 plus 1. So 2 on this neighboring carbon here plus 1. That's going to have a triplet. So what we see here is we see that these here are split into 4 different peaks, but those peaks themselves, so we have a splitting into a quartet, but then we have each part of the quartet is a triplet. And so this is an example of a complex splitting pattern that can occur if you have splitting due to hydrogens on carbons that are on either side of a pair of hydrogens that have significantly different chemical shifts and are in different chemical environments. We have a quartet of triplets here. Complex splitting results when a proton has 2 different chemically distinct neighboring protons with significantly different chemical shifts. If JBC, the coupling constant between B and C, is much greater than A and B, then the signal will appear as a triplet of quartets. So the primary splitting here would be a triplet due to the two hydrogens on the HC, but then the secondary splitting would be into a quartet with smaller J coupling values. So you see that triplet of quartets. If JBC and JAB are very similar, then you will not see this complex splitting. So here, the reason this splitting is so complex is because the chemical environment for these guys right here is very different than the chemical environment for the HAs because they're right next to a halogen atom, which is de-shielding these significantly. And so you end up with a much larger chemical shift for this one. For the protons labeled A here, you have a much smaller chemical shift. But assuming that you have a different molecule, like let's say you had a really long molecule like this one, and you had these two hydrogens right here, well, these hydrogens are not going to be split into a triplet of a triplet because the chemical environment for this carbon is going to be essentially the same as this one. So these guys would actually split into 4 plus 1, 4 hydrogens plus 1. You would get a quintet signal for this one because these hydrogens are not only chemically equivalent, but they're also in similar chemical environments and electronic environments. And so you would just get one signal from it. So this complex splitting only occurs when you have protons on neighboring carbons that have significantly different electronic environments. Splitting is not observed for some protons, particularly those in alcohols. So in the examples that we're seeing in lab, you have a proton here, and those tend not to be split by the protons here. So if this is, we're going to call this here, this is going to be in terms of the splitting here. Yeah, we're going to have a splitting that is different, right? We have the proton, this one here. We have the chemical shift here. Notice the chemical shift is very low for this one, which is called number 3. It's split like a triplet. This one is number 3, and it represents 3 protons too, so that's why it's larger. Okay, and then we have the protons on the carbon attached to oxygen. These are number 2, and these get a significant chemical shift being on the carbon attached to the oxygen. And then we have this last one here, which is this one, which has a chemical shift around a little over 2. And remember, these alcohol protons, they range from about 2 to 5. But it's still shifted downwards because of this association with alcohol. So notice that the protons bonded to carbon split each other, but the hydroxyl proton is not split here. And it does not cause any splitting either on carbon number 2. The reason why this is because there's basically a basicity to this alcohol, a mild basicity. So if there is any proton, any acidic or basic environment, you're going to have a movement on and off of protons, which is going to blur the signal here and make it so that splitting is not, the neighboring protons here are not going to experience that shielding, de-shielding effect constantly. And so what you see here is this, for example, this oxygen can be protonated. If there's the tiniest bit of acid, it will do a proton transfer, and then a water can come by and remove it. And so we have this constant interchange of protons going on. And what that means is that this proton here does not split the neighboring protons because it's not always there. It's constantly being moved around. We say that these protons are labile or exchangeable, those that are attached to the oxygen. So if we have here these three, so to show you what is the value of NMR, if we took an infrared spectrum and a mass spectrum of these three molecules, so we have here 1-methyltoluene, or it's also called metatoluene. We have orthotoluene. We have paratoluene. And so these are all going to give similar fragmentation patterns in mass spec. And they're going to give the same IR spectra, essentially, because they all have the same types of functional groups. But with NMR, we can easily tell the difference between these because they do not have the same number of equivalent protons. If we have this methyltoluene, we'll have these 6 protons, which are chemically equivalent. These 2 are chemically equivalent, and these 2 right here. So we'll get 3 separate proton signals. However, if we have orthotoluene, we'll have these 6 protons, which are chemically equivalent. This 1, which is chemically equivalent to nothing else. These 2, which are chemically equivalent to one another, the blue ones. And then finally, this proton here, which is not chemically equivalent to anything. We'll have 4 different chemically equivalent groups of protons, so we'll get 4 signals. However, if we have para-methyltoluene, we'll have these 6 being chemically equivalent on the methyl groups, and then we'll have these blue protons be chemically equivalent to these blue protons on the other side. So we'll only get 2 signals. So it becomes very obvious based on the number of proton signals that we get which of these structures we have. And that's something that just can't be done with infrared spectroscopy or mass spectrometry alone. So finally, putting it all together, and something we've practiced in lab is if we have a molecular formula, which we can get from the mass spec usually in the molecular ion, and we have a proton NMR spectra, we can often determine the molecule structure, especially if we have an infrared spectrum to support it and confirm what we think the functional groups are. So we're going to calculate the degree of unsaturation, which your book also calls the hydrogen efficiency index. Remember that a molecule that has basically hydrogens that are twice the number of carbons plus 2 more, these are considered completely saturated, and they have a DOU of 0. For every 2 less hydrogens we have, we get a DOU of 1. And one DOU, a DOU it represents a pi bond or a ring. One DOU is pi bond or a ring. And remember that when we're making this comparison, for oxygen, we don't have to make any adjustment, but if we have a nitrogen somewhere in the formula, then we need to remove 1 proton to make a direct comparison, because this nitrogen has this extra proton. Whereas if we have a halogen atom, to make the comparison accurately to the saturated hydrocarbon, we should add a proton for every halogen atom. And then we compare, and for every 2 that we are short, then we consider that 1 degree of unsaturation. And so this will help us to confirm the molecular formula. Finally, we consider how many NMR signals and see if that agrees with the number of chemically equivalent protons that we have. We analyze each signal. We draw fragments that might be consistent with each signal. For example, we saw really obvious patterns that correspond to isolated ethyl groups and isolated isopropyl groups and isolated tert-butyl groups and so on. So those can give us insight into fragments of the molecule. Finally, we try to put those fragments together that makes a complete structure that is still consistent with the NMR. And finally, we verify that its structure is consistent by trying to assign each peak to the proton NMR. So that's proton NMR spectroscopy. Another valuable type of NMR spectroscopy is going to be the carbon-13 NMR spectroscopy. So because protons are by far the most abundant isotope of hydrogen, you're going to get strong NMR signals. But carbon-13 is only 1% of the carbon atoms in nature. So you're going to need a very sensitive receiver. You're going to need a concentrated NMR sample, not diluted too much. In proton NMR2, we're going to be really considering the splitting uh, and the integration. However, the integration, because of the weak signals in proton NMR, the integration is not always reliable. So what we're mostly concerned with proton carbon-13 NMR is the number of signals and the chemical shift. So in carbon-13 NMR, the uh, the the proton and carbon-13 splitting is very complex, and so the spectra are often taken in a way that those won't be seen. So we do a so-called decoupled NMR, which makes it so that we don't have a significant splitting seen all over the place for the carbon-13. So in most carbon-13 spectra, unless another technique is used, the carbon atoms are all going to be represented by singlets. And compared to proton NMR, carbon-13 atoms, they will require a different frequency to resonate. So whereas for proton NMR, the chemical shifts generally ranged from 0 to 12, 0 to 12 ppm for the chemical shift. For carbon-13, it's going to be between 0 and 220 ppm. And each signal will represent a chemically distinct carbon. So chemical equivalence, just like for hydrogens, it's the same for carbons. So we can use planes and axes of symmetry to analyze and see whether carbons are electronically equivalent or chemically equivalent. So for example, here, if we have the meta methyltoluene. Here we're going to get 4 chemically distinct carbons, one on the methyl, and then one on each side of the ring, with this being the plane of symmetry. So these are all, these ones are chemically equivalent to these ones, this one chemically equivalent to this one, and so forth. If we have orthometabenzene, or orthomethyltoluene rather, we're going to have 5 unique proton signals, because this carbon is no longer the same as this one, right? So in terms of chemically equivalent, this one is chemically equivalent to this one. This one here is chemically equivalent to this one, and this one is chemically equivalent to this one. But this one is 2 spaces away from the methyl. This one is only 1 space away. So these are not chemically equivalent to one another. They give you 2 separate signals. When it comes to the para-methylbenzene, here we have only 3 signals, because the carbon signal here is chemically equivalent for this carbon here. This carbon is chemically equivalent to this one here. And then these 4, this one is chemically equivalent to this one, and this one. They're all chemically equivalent. So those are all going to give us 1. Like the proton NMR signals, chemical shifts for carbon signals are affected by the shielding and deshielding. Generally, if you have a carbon that's a part of a carbonyl, again, that one's attached to a very electronegative atom. It's also got electrons that are participating in pi bonding and giving this anisotropic effect. So it's going to be ketone and hydrogen carbons that have the greatest chemical shift. Then carboxylic acids next. This is because the oxygen kind of pulls the electrons a little bit in the other direction. You don't get as much deshielding from the 2 oxygen atoms attached. Finally, nitrogen is much less electronegative than oxygen, so that decreases the effect there. Aromatics are going to have the significant anisotropic effect, so you're still going to get a significant chemical shift for those carbons. Those carbons that are vinylic, directly attached to the carbon-carbon double bond, also a significant chemical shift, and then less so for carbon-carbon triple bonds, and so forth. The more electronegative atom in a single bond that the carbon is attached to, the greater the inductive deshielding effect is. Now, a few other notes about other types of NMR spectroscopy. We're not going to do these ones in class. These are more advanced techniques that are generally used in research. Carbon-13 spectra will give singlets that don't provide splitting information. However, there are other techniques that can be used to get some of that splitting information. One is called distortionless enhancement by polarization transfer, or DEPT. DEPT C13 NMR will actually get you some splitting information. There's two modes to this DEPT. One called DEPT 90 shows only CH signals, so carbons attached to one hydrogen. DEPT 135 has positive signals for carbons attached to odd numbers of hydrogens and negative signals for carbons attached to even number of hydrogens. So when it comes to the normal broadband decoupled NMR spectroscopy for carbon-13, you're going to get singlets no matter what the carbon is. If you do the DEPT 90, you'll get no signals for anything but the carbons attached to one hydrogen, and you get a positive signal for that. If you do the DEPT 135 technique, you'll get no signals for carbons attached to 0 hydrogens. But for carbons attached to 3 hydrogens or 1, you're going to have positive signals. And for carbons attached to 2 hydrogens, you're going to get a negative signal. Finally, nuclear magnetic resonance is also used in medicine. And so it can be used to detect certain isotopes in the body. And when it's done in medicine, it's called magnetic resonance imaging. They're essentially proton NMR spectrometers, but situated in such a way as they can do this. They can essentially put you inside the magnet as a sample rather than a little sample. So they're like a very big NMR spectrometer. And different tissues are going to have different concentrations in protons. And depending on those concentrations of protons, we can see the environment of that part of the body. And so the MRI ends up giving a 3D image of different tissues. And the radio waves and magnetic field are quite small, so you don't really experience anything. It's not like being exposed to damaging radiation. Radio frequency waves are very low in energy, so they're not dangerous. And so that's kind of the outside application, outside of chemistry. So at this point, we've completed our lectures for this week. We've seen the powerful technique of nuclear magnetic resonance for determining the structures of molecules. As particularly useful is the proton NMR, in which we analyze the chemical shift and the splitting pattern and the integration of the peaks to figure out how many protons they represent, where in the structure those protons lie, and what are the neighboring carbons that we can determine via the coupling and the splitting patterns. Then we saw also carbon-13 NMR, which generally will be decoupled and will produce a singlet for each chemically distinct carbon, and that can give us further confirmation of what we observe in the proton NMR. And finally, we saw a couple of applications here, such as DEPT, carbon-13 spectroscopy, and the medical application of magnetic resonance. So most of your homework this week is all practicing those packets where you're given a molecular ion, you're given a IR spectra and a carbon-13 NMR spectrum and a proton NMR spectra, and you're asked to identify the molecule. And these are real-life types of identifications that people make with molecules that they synthesize in the lab, even new molecules that have never been seen before. So I think it's a super interesting, super powerful technique, and if you're interested in synthetic chemistry, it's the most powerful analytical technique that you have at your disposal. I hope you enjoy those difficult problems, but let me know if you get stuck, and I hope you have a great week. I will see you at the next lab. Have a good one. Bye-bye.